Good morning, everyone. Thank you for joining us for the webinar on transforming register-based logic into a UDFB. The presentation itself is roughly about 17 minutes or so, and if you have any questions, you can put them in at any point and we'll get to them at the end.
Hello and welcome to today's webinar. Let's get started. Let's look at our agenda for today. Today we're looking at transforming your register-based logic routine into a user-defined function block, or UDFB. So let's break down our topic for today. We'll start with a review of the differences and similarities between register-based and variable-based advanced ladder. We'll look at the advantages of a user-based function block, but mainly we'll be talking about the workflow when you're transforming the register-based logic routine into a UDFB. We'll have demonstrations throughout, and we'll finish with a Q&A session. In Cscape, there are multiple types of logic programming available. There are the two variations to advanced ladder logic, which are register-based and variable-based, but it also supports the IEC 61131 languages. Today, we'll really be focusing on advanced logic ladder, or American-style advanced ladder as it's sometimes called. We'll start with register-based advanced ladder. Register-based advanced ladder was the original logic language available in Cscape in 1998, and is still the most widely used style of Cscape logic today, with no plans to obsolete it. There are some disadvantages to register-based advanced ladder, however, because it requires that all variables that you add to your program have to be mapped to a specific memory address in the program, which makes it more labor-intensive. It is also more labor-intensive when you are replicating code, because every time you copy and paste, you have to go into the pasted logic to readdress everything. It also doesn't support some of the newer features, for example the data structures and the user-defined function blocks. With variable-based ladder logic, you don't have to map all the variables as you add them. You usually only need to deal with a few of them, and you do get support for the newer features. In Horner training, both variable and register-based are taught in the same course, although the advanced course is focused on variable-based. For inexperienced users that are getting familiar with Cscape, variable-based is recommended. But if you have used register-based for years and want to reuse that code, you can convert your program from register to variable-based. Now we'll take a look at memory mapping between the two. With register-based advanced ladder, you have to map every variable as you bring it in. With variable-based, you don't, unless you have a real-world I/O point and you want to tie a variable to that real-world I/O point, or you're going to send a variable out over a network like Modbus. In one of those cases, you would memory map. Now, the tools are a bit different between register-based and variable-based when you're creating and editing variables. Both can be created either on the spot or in advance, but the tools themselves are a bit different. As we said already, today we're going to be talking about user-defined function blocks. These are sections of code that we can take and modularize and turn into a function block that can be called, similarly to a subroutine. Unlike subroutines, with UDFBs there can be multiple instances in the same program. If you're using a subroutine, you will only have one copy of the given subroutine, and you can only call that subroutine once at a time. For example, if you're going to create a user function block to do some single pump control, and you have a dozen different pumps in your application, you create a single UDFB for pump control. So then you basically have 12 different instances of that UDFB for each pump. That's something you can't do with subroutines, because with UDFBs, each instance has its own set of variables. There are lots of benefits to UDFBs. For example, the ability to reuse code very easily, how they make programs more organized and easy to follow, and the way a routine that would normally need to be repeated multiple times in the same application instead can be called multiple times, and that each instance has its own set of variables, meaning that each instance can be in a different state at any given time. We'll just talk for a minute about what our workflow would normally be to create a UDFB. If we're starting from a variable-based advanced ladder and we want to take some of the logic we've already written and turn it into a UDFB, the procedure is just there on the screen. We are going to cover today in a lot of detail how to take a routine of logic that could have been written years ago using register-based logic and turn it into a user-defined function block that can be used in a new variable-based program. There are a lot of advantages to this approach that we'll look at today. Firstly, if you've been using register-based logic for years, you probably have a lot of code that you've written and tested and that you'd like to reuse if you can. And by reusing sections of logic instead of the whole program, the heavy lifting of code creation and testing has already been done. By taking a section of code, it's quite easy to turn that into a user-defined function block, so that's what we'll be focusing on today, mainly through demonstrations. So, this is the workflow we're going to demonstrate step by step. So, we start by isolating the piece of program that we want to turn into a UDFB. We go in and check that it's documented the way that we want, Then we convert that little snippet into a variable-based program on its own. We get rid of any memory mapping that happens by default when it's converted from register-based to variable-based, because we never use mapping when using or creating user-defined function blocks. We identify the inputs, outputs, and private variables that we need to specify when we create our user-defined function block. Then we create the user-defined function block and test it. Now we'll have a demonstration of our workflow using the steps we just looked at. So the first step is to isolate the code that we ultimately want to turn into a UDFB from the register-based program it was originally included in. So this is the application which is performing a 3-point calibration while it also scales an analog input to engineering units. So here's the logic. It's only about 30 lines of code and we can see that it's register-based logic. Then there's a screen or user interface where you can see how it's designed to work. So the idea is that in the field you would have a technician who would fill in the low, the middle, the high levels that you want to calibrate to, and those would be engineering units. Then during the calibration process you can monitor the raw analog input coming in, and then after the levels were set and the calibration was complete, the scaled values would be here and could be used to verify the scaling was correct. So that's how the application works. Now this is where you would download it, but we actually already have it downloaded, so instead we're going to go take a look at how it's working. It's important to test the code that you're going to turn into a UDFB to make sure it's working before you turn it into that block. So we'll use 2 meters, 7 meters and 10 meters from the well level here, which are our engineering units and inputs to the code. So we'll move the analog value up to what would be the 2 meter level, then press set low calibration. Then we'll move up to what would theoretically be the 7 meter level and set that. And now we're done and we're getting the results we want. We can see the scale value here is working. So that's the code that we've isolated that we're going to turn into our user-defined function block. So now we'll look at the variables and the comments in our program and make sure we're happy with them. We can see that the IO names that were put in here originally reference specific channel numbers and things like that. They're also quite long, whereas when we're creating variable names to be used for UDFB, we want them to be more generic and a bit shorter. So we go to program and then IO names, and we're going to rename these variables to be more generic and concise, which is an optional step. One of the things you can do in Cscape is you can copy all your variables and then paste them into Cscape, which we have done already. Here on the spreadsheet we can see the original variable names or IO names. Now we need to decide what we want their names to be, names that would be preferable for a UDFB. Then we create a new set of names here, and then we have the ability to copy the new names and go back to Cscape and to the program IO names area and paste them in. Again, an optional step, but it makes things easier. The next step in our workflow is to convert the register-based logic over to variable-based. So let's do that now. To do this, we go to the project navigator, highlight the name of the program, right-click and select Convert to Variable-Based. We hit the Start button. It immediately prompts us for a new program name. So we type in the new name, press Save, and it completes the conversion process. The size will be larger, but it won't be a problem. At this stage, it's important to save because we now have the variable-based program that we want to save. Once we've done that, the next step is to strip off the memory mapping that is maintained when you convert from register-based to variable-based because we don't need it anymore. Sometimes you might want to leave the memory mapping there, but not when you are creating user-defined function block. Firstly, we're going to close that program that we just saved and then reopen it. That way, all the options for a variable-based advanced ladder program, including the ability to create UDFBs, will be present because Cscape knows that this is a variable-based advanced ladder program. So now I'll open the program variable window. Remember, the variable window is the tool used to edit variables in variable-based advanced ladder. So we go on to the global variables, and this is where we see the global variables that have been created. And you'll notice that when we get to here, we've got the memory mapping. And that's what we'll strip off because we don't need that. So we double click on the memory column, press the backspace to clear it out, and then enter. And we're going to do that on every variable, and that is the next step in the workflow. So we have our new program here, which has been converted from register-based to variable-based, and has memory mapping stripped from all the variables, as you can see here. Firstly, we'll create the UDFB by going into UDFB modules, right-clicking, selecting new UDFB, and giving it a name. We'll call it cal_3point, as it should have quite a short name. Then we need to create the variables for the UDFB, because UDFBs have their own variables. So let's go back to our program variable window. And you can see now that this UDFB has been created with a variable group called cal_3point. So now we'll add a few variables to it. So we right click and press add variable and we'll make it an input parameter. And we know that one of the inputs to the function block is going to be the AI in, which is an integer value. And we'll add an output. We know one of the output variables is scaled output, which is a real variable. Now we look at a shortcut for doing this. Firstly, we go to the global area. That's where all the variables that were created in the main loop that will ultimately become UDFB logic are. Here, we right-click and press Edit Variables as Text. And then we can scroll down and find that list of all the variables that will be in the UDFB. So we copy those, close it, and go down here where we right-click and say Edit Variables as Text. Then we edit the variables as text for the calibration variables. And then we'll paste in all these variables that need to be classified here. Now we need to add the syntax for the private variables. We'll get rid of AI in because we already did that one. Low, mid, and high EU are the engineering units, which are input variables. Scaled is an output, so we move that. We put all the internals where they need to go, and finally put the inputs in the input section. So we have inputs, output, and internals, and that's a shortcut for getting all those variables added. The reason we can do that is because we keep the same names. So now we have variables assigned to the cal_3 UDFB. Now we want to take all the code that is in the main loop and insert it into a UDFB loop. We have about 30 lines of code, so we have to make sure we have enough room for it. So we go back to the UDFB area and add 10 lines first and then 20 lines to make sure. Then we go back to the main code, we select all and copy. Then we go to cal3, click where we want to paste it and then paste. So we've just pasted in code with all the variable names from the global area. Inside of a UDFB, for all UDFB variables, they have the prefix of the name of the UDFB. So we'll add that now using another shortcut. We'll paste in the prefix on all these variables' names. Firstly, we'll select from the cal3 group the AI_in variable, and you can see it put a prefix on here. So then we copy that prefix and paste it on every variable that's using a UDFB variable using Ctrl+V. This should take less than 5 minutes. We've sped up the process here, but basically you're going into every function block under every variable that's using a UDFB variable and pasting that prefix onto it. Once that's done, we have logic in our UDFB using the proper variables. Now we need to test this. So we go to the main loop, which has the original logic in it, and we don't want this to execute. So instead, we right-click and select Exclude from Compilation. So now this original main route, when I run my program, isn't going to execute. But now we'll create a new main loop module and call it test UDFB. Now we're actually going to build logic using the UDFB and make sure everything works properly and test it. And to do this, we'll use an always on contact. And now we'll call an instance of the UDFB. If we go to the project toolbox, we can see that there's a section called UDFB at the bottom, and the cal3 UDFB is listed there. Now it'll ask us to name it. Let's just say this is the level of a tank. We'll just call it level cal. Now we need to fill in what the inputs and what the output variables were for the UDFB. Now the way we've done this, we already have global variables with those exact names that can be used as the inputs and outputs for our user-defined function block. So we can just choose them from the list or type them in. If they're typed in properly, because they already exist in the global list, it should just take them. If it asks if you want to create a new variable, that probably means that something has been typed in incorrectly, but these all seem okay. So here's our user-defined function block. To test this, we can just download it to the controller. So now we'll do the test. One thing we can't forget is that this AI_in variable, to be tested on the bench, needs to actually be mapped to one of the analog inputs in our system or in the I/O simulator. So in the global variables list, we added a memory mapping entry for %AI1, so that way we are getting direct correlation between the analog input coming in and this particular variable. The other thing we can do when we make a significant change to a variable-based program is to actually clear the memory in the controller before downloading the new program. That way we can be sure there won't be any old variable values. So one of the ways we can do that is under controller and then clear memory. So now we'll clear out our program and register on variable values. It reminds us here that the controller is now stopped, and so we'll go ahead and do the download. Once the download is complete, we must remember to restart the controller. So now we'll set our low, mid and high engineering units. We've been using 2 for low, 7 for the mid value and 10 for the high value. We are getting a value here for our raw input because we mapped it to our first analog input. We'll set it up here to what we're calling the 2 meter level. So that's our low calibration point. We'll set it up higher to approximately what we're calling the 7 meter level. In a real application, we would be very sure it was exactly 7 meters. And then we'll go ahead and go up to what we're going to call, for the purposes of this demonstration, the 10 meter level. As the level goes down and the analog signal goes down, we can see that the analog scaling is doing exactly what we want, and that we've effectively calibrated our analog input with a 3-point calibration method. And at the same time, we scaled it to engineering units, so that's complete. Now we have one last step after we have completely finished and tested our UDFB, and that is exporting this UDFB so that it can be used in future projects. So we highlight here and right click and press export, and then it asks if you want to export the module fully protected, which we wouldn't recommend unless you're at the point where you don't want whoever's using this UDFB to see the logic inside. So we're going to say no, which will mean that we can see the logic inside. Then we'll give it the same name, cal3point, and it'll have an extension of CPU. We save that, and now the next time we have a new variable-based advanced ladder project and want to use that 3-point calibration method, we can just import that UDFB into the project. And then we have the availability of using that with multiple instances within that project. So if there are 4 analog inputs, we can have 4 instances of that UDFB. Before we finish, we'll look at how to import a UDFB into a project. So we're going to create a new variable-based advanced ladder program. Even though it could be an existing one, it doesn't have to be a new one. Then we'll import that UDFB into this program. So under Logic Modules, we right-click and select Import Logic Modules. Go to the folder that contains the CPU file and press star.cpu so that Cscape can find the file. Now we press open, and it's showing the contents of the UDFB because of the fact that we didn't protect it when we exported it. And now, in the main loop or any other main logic module, we can find that UDFB under the UDFB area of the toolbox. And then we can place it in our project, name it, and use it. So that's our final demo for today. So, as we've seen today, user-defined function blocks are an amazing feature, whether you're talking about variable-based advanced ladder or whether you're looking at the IEC 61131 programming languages. It's available in any variable-based language in Cscape, and just because you have a piece of code that was originally written in register-based advanced ladder, it doesn't mean that you can't turn that piece of code into a user-defined function block. So that concludes today's webinar. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, hopefully that will be of good benefit to you now. I'm not seeing anything in just now, so next week's webinar is building an analog totalizer. So if that does sound of interest to you, the registration link is up on the webinar page as usual. Have we got something coming in? I think we have a question in. A screen call at the end of a rung. Yes, we can do that. So is it possible to have a screen call at the end of the rung? Yes, as we do in ladder. Oh, sorry. I believe so. I'll double check that. I'll link up with you directly after. Okay, I'm not seeing anything else in. But yeah, so that webinar is up for next week, and the registration link is there as usual. Thanks all for joining this morning, and we do hope to see you again next week. Have a good day.